Ninth episode on aldehydes and ketones, and in this we are going to discuss sixth lecture on reactions of aldehydes and ketones. In the earlier lecture we have discussed condensation reaction like aldol condensation and Cannizzaro reaction. Under the category of aldol condensation we discussed the crossed aldol condensation and intramolecular aldol condensation, and then we discussed its application also. And in under the category of Cannizzaro reaction we had discussed cross Cannizzaro reaction, intramolecular Cannizzaro reaction, and then some applications of Cannizzaro reaction. So, to start with today's lecture, in this lecture we are again going to discuss some of the reactions given by carbonyl compound. First of all, we will discuss Beckmann rearrangement, we will discuss its mechanism, then we will discuss the application of Beckmann rearrangement. The next reaction which we will discuss here will be Novengiel reaction, the mechanism of Novengiel reaction, and then the application of Novengiel reaction in synthetic organic chemistry. The next reaction that we will discuss here in present lecture is Reformatsky reaction, the mechanism of Reformatsky reaction and application of Reformatsky reaction. And lastly, we will discuss Tishkienko reaction and its mechanism. So, to start with Beckmann rearrangement, this reaction is given by the oximes of aldehydes and ketones. The reaction of ketones with hydroxylamine results in the formation of ketoxymes. Ketoxymes in presence of acid catalysts such as phosphorus pentachloride or sulfuric acid or phosphorus pentaoxide or BF3 or thionyl chloride or sulfur trioxide undergo rearrangement to form N-substituted amides. The reaction is called Beckmann rearrangement. Here you can see that this is the ketoxyme resulted by the reaction of a ketone with hydroxylamine undergoes reaction in presence of thionyl chloride to give N-alkyl amide. We will now discuss the mechanism of Beckmann rearrangement. In the first step of mechanism of Beckmann rearrangement, it involves the generation of electrophile by the protonation of the hydroxy group. You can see here that this hydroxy group is protonated. There is formation of protonated oxime which is followed by the removal of water molecule and an electrophile is generated. In the second step, 1,2 alkyl shift takes place where the alkyl group with its pair of electron migrates to adjacent electron deficient nitrogen and generates a carbocation. You can see here we have here 2 alkyl groups attached to carbon next to electron deficient nitrogen. So, this alkyl group with its pair of electron moves or migrates to this electron deficient nitrogen. As a result, there is formation of electron deficient carbon which we call as carbocation. The third step involves hydration at the electron deficient carbon followed by proton transfer. This is the electron deficient carbon. Water molecule attaches the lone pair of electron on oxygen actually attach the water molecule at this electron deficient carbon followed by removal of a proton and then the proton transfer to generate N-alkyl amide, the product in case of Beckmann rearrangement. The Beckmann rearrangement is highly stereospecific reaction. The migrating group always approaches the electron deficient nitrogen from the side opposite to oxygen atom. You can see here that here we have this hydroxide group, we have these 2 alkyl groups. The stereospecificity of the reaction is that only the alkyl group which is on the opposite side of this hydroxide migrates, not the other one which is on the same side of hydroxide. As a result, a definite product is formed in Beckmann rearrangement. Before we discuss the product of Beckmann rearrangement, first of all we should understand what is syn and anti-oximes. In oxime chemistry, the term syn and anti are used instead of cis and trans. In case of aldoxime, syn form is the one in which hydrogen and hydroxide are on the same side, When these groups are on opposite side, then the configuration of aldoxyme is called NT. In case of ketoxyme, the prefix indicates the relationship between first group named and the hydroxyl group. For example, you can see here in this compound, this is a ketoxyme and compound 3 is named as syn-para-tolulyl phenyl ketoxyme. Syn because this para-tolulyl phenyl group is syn or on the same side of hydroxide group. The same molecule is also called anti-phenyl para-tolulyl oxime, that is this hydroxy group is anti to phenyl group. Now, E and Z system is also applied to oximes. The syn oximes of benzaldehyde are classified as E or anti-oxime of benzaldehyde are named as Z isomers. Now, the anti or Z isomer of oxime of acetophenone upon Beckmann rearrangement forms N-phenyl acetamide almost exclusively, whereas the syn or E isomer of oxime of acetophenone forms N-methyl benzamide. As you can see here in this example, that this is the anti or Z isomer of acetophenone. This molecule is the Z isomer or anti isomer of acetophenone, and since the phenyl group is anti to hydroxide, so this phenyl group migrates. As a result, there is formation of N-phenyl acetamide formation takes place in this particular reaction. Whereas, when Beckmann rearrangement is done in syn or E isomer of acetophenone, now you can see the hydroxide group is anti to methyl group. So, in this particular case, following the same sequence of reaction, methyl group will migrate to electron deficient nitrogen. As a result, there will be formation of N-methyl benzamide. So, you can see that different isomers of the same aldehyde are forming different products as a result of Beckmann rearrangement, and this shows the stereospecificity of this rearrangement. In case of syn and anti isomers of oxime of phenyl paramethoxyphenyl ketone, Beckmann rearrangement form different products. As you can see, these two are the syn and anti isomers of the oxime of same ketone, and they form different products upon Beckmann rearrangement. The anti-benzaldeoxime, that is the oxime derived from benzaldehyde, undergoes Beckmann rearrangement in presence of polyphosphoric acid, also called PPA, to form benzamide. You can see here, this is the anti-benzaldeoxime having hydroxide and hydrogen at anti to each other. As a result, hydrogen migrates to electron deficient nitrogen and there is formation of benzamide take place. In case of syn isomer, we have seen that even though hydroxide is anti to phenyl, as a result the product should be N-formyl amine should be formed, but we get a definite amount of benzamide also, and the reason is because there is conversion of this syn isomer into anti isomer during the process, which then undergoes migration of hydrogen and forms this result. So, in case of Beckmann rearrangement of syn isomer, there is formation of mixture of products. We will now discuss the application of Beckmann rearrangement. This rearrangement is used to synthesize nylon 6 from cyclohexanone oxime via cyclic amide, commonly known as caprolactam. This is caprolactam. This is formed as a result of Beckmann rearrangement of this oxime, the oxime of cyclohexanone. Starting from phenol, first of all we can prepare this cyclohexanol by drastic hydration, followed by oxidation to form cyclohexanone, and then the cyclohexanone is converted into its oxime, undergoes Beckmann rearrangement, and this caprolactam then polymerizes into nylon 6. And this is a very important application of Beckmann rearrangement, where this rearrangement is used for the preparation of a commercial product like nylon 6. The reaction is also used to determine the configuration of ketoxymes because syn and antioxymes give different products upon Bergman rearrangement. The amides so formed can be characterized by their hydrolysis. Here you can see that different ketoxyme, syn and anti, different ketoxyme of the same ketone undergo Bergman rearrangement and form different products, and they can be identified by their hydrolysis. This product upon hydrolysis gives a different acid as compared to the other product. So, with the help of Bergman rearrangement, we can identify the nature of carbonyl group from which we have undergone this Bergman rearrangement. Phenyl cyanide can also be prepared from the oxime of benzaldehyde, and phenyl cyanide then is used in a number of applications. We will now discuss another condensation reactions undergone by carbonyl compounds and is known as Novengiel reaction. In this reaction, the condensation of carbonyl compound takes place with compounds having active hydrogen. These kind of compounds are also called active methylene compounds. The reaction takes place in presence of base and the reaction is called Novengiel reaction. The catalyst used in the reaction is normally an amine which may be a secondary amine or a tertiary amine, but it has been found that best results are obtained with secondary amines. Carbonyl compounds having no alpha hydrogen are used for the reaction. Beta hydroxy esters are formed in this reaction. As you can see here, this is an aldehyde having no alpha hydrogen and this is diethyl malonate compound which has active methylene group. Active methylene means hydrogens are acidic. As a result, there is formation of this unsaturated ester. Now we will discuss the mechanism of Novengiel reaction. In the first step, the secondary amine base which is used as catalyst abstracts a proton from active methylene compound and generates carbanion. This is the base abstracts a acidic hydrogen from active methylene compound and generates the carbanion. In the second step, carbanion generated from active methylene compound attacks the carbonyl carbon of aldehyde having no alpha hydrogen, followed by proton transfer from a protonated base. You can see here this is benzaldehyde, does not have any alpha hydrogen, is attacked by carbanion generated from active methylene compound, and in the next step the proton has been transferred to this alkoxide by the protonated base. The third step involves the dehydration of beta hydroxy ester. This is a beta hydroxy ester which undergoes dehydration to form alpha beta unsaturated esters. Compounds having active hydrogen are active methylene compounds like ethyl acetoacetate or diethyl malonate or a malonic ester which undergo Novengiel reaction. It has been found that compounds like alkynes, haloform, cyclopentadiene and nitroalkanes also have active hydrogen and thus undergo Novengiel reaction. Cyclopentadiene has pK value of 16, that is, it is acidic enough to form a carbanion by abstraction of proton by a base, and then it forms 6,6-dimethyl fulvene upon reaction with acetone. You can see here that this is cyclopentadiene and here we have this active methylene group which forms a carbanion and then undergoes reaction to form this 6,6-dimethyl fulvene in almost 75% yield. Here in this reaction we have shown the mechanism of reaction of cyclopentadiene with acetone. This cyclopentadiene is first converted into its anion and anion then attack the carbonyl carbon of acetone. As a result, this fulvene is prepared. Now we will see how ketones react to this Novengiel reaction. It has been found that ketones are less reactive than aldehydes, hence undergo the reaction with compounds having highly activated methylene groups like ethyl cyanoacetate. This ethyl cyanoacetate can undergo Novengiel reaction with ketones. We have said that these are highly active methylene compound. Why they are highly activated? Have you any idea about it? You can see here that this is cyano group, which is highly electron attracting group, as well as we have a carbonyl group here also. So, since this methylene is flanking or present between two highly electron withdrawing group, this CH2 or these hydrogens become highly acidic in nature, and that is why this kind of molecule undergo Novengiel reaction with less reactive ketones also in very good yield of about 80%. Both aliphatic and aromatic aldehydes undergo Novengiel reaction. Ketones are less reactive because of steric and electronic factor, hence require powerful active methylene compounds like ethyl acetoacetate and ethyl cyanoacetate. Ketones do not react with malonic ester. So, here again we have an example which is forming the Novengiel product, which upon hydrolysis forms this 3-methyl crotonic acid. Now, we will discuss some application of Novengiel reaction. The alpha beta unsaturated ester formed during the course of Novengiel reaction undergoes Michael reaction in presence of excess of active methylene compound. The product after hydrolysis and decarboxylation forms 3-methyl glutaric acid, a dicarboxylic acid. You can see here this 3-methyl glutaric acid is formed as a result of reaction of this Novengiel product with another molecule of active methylene compound. So, this reaction from here to here, this reaction is called Michael reaction. Novengiel reaction is also used for the preparation of alpha beta unsaturated carboxylic acid. Alpha beta unsaturated ester undergo hydrolysis and decarboxylation to form alpha beta unsaturated carboxylic acid. Ethanol reacts with malonic ester to form crotonic acid by the following sequence of reaction. You can see this is acetaldehyde reacting with diethyl malonate, forming this alpha beta unsaturated ester, which upon hydrolysis and decarboxylation forms crotonic acid. Benzaldehyde reacts with malonic ester to form cinnamic acid by following this sequence of reaction via Novengiel reaction. Glyoxylic acid reacts with malonic acid to form maleic acid and alpha beta unsaturated dicarboxylic acid. This is glyoxylic acid reacting with diethyl malonate, forming this Novengiel product, which upon further hydrolysis and decarboxylation forms maleic acid. We will now discuss Reformatsky reaction. The carbonyl compounds react with alpha haloesters in presence of zinc to form beta hydroxy esters. Acetaldehyde react with ethyl bromoacetate in presence of zinc to form ethyl 3-hydroxybutanoate beta hydroxy ester. Acetaldehyde reacts faster than ketone. I think you know the answer. We have repeated this question again and again that acetaldehydes are more reactive than ketones because of the less steric factor and more electrophilicity of the carbonyl carbon. In this example, we are starting with ethanol or acetaldehyde reacting with bromoethyl acetate to generate this ethyl 3-hydroxybutanoate, a beta hydroxy ester. Propanone reacts with bromoethyl acetate in presence of zinc and forms ethyl 3-hydroxy 3-methylbutanoate as the product. In another example, ethyl 2-methyl 2-bromopropanoate reacts with ethanol in presence of zinc and forms ethyl 3-hydroxy 2,2-dimethylbutanoate as the product as a result of Reformatsky reaction. Reformatsky reaction is also given when carbonyl compounds react with alpha halocyanides in presence of zinc in ether solution, followed by hydrolysis to form beta hydroxycyanides. Benzaldehyde reacts with 2-chloroethane nitrile in presence of zinc to form 3-hydroxyphenylpropane nitrile, as can be seen in this figure. Reformatsky reaction is also given when carbonyl compounds react with alpha bromo NN dimethyl acetamide in presence of zinc in ether solution, followed by hydrolysis to form beta hydroxy amide, as you can see in this figure. We will now discuss the mechanism of Reformatsky reaction. The reaction proceeds via the formation of organose zinc compound, which provides carbanion for nucleophilic addition. As you can see here that this is bromoethyl acetate reacting with zinc and forming this organozinc compound. There was a bond earlier between carbon and bromine. Now there is a bond between carbon and zinc is then attached to bromine. So, this type of compound are called organometallic compound or organozinc compound. Now, the beauty of these compound is that now in this case, if you will look at the electronegativity of carbon is less than that of bromine. If carbon bromine bond breaks, then there is formation of a carbocation, but when carbon zinc bond breaks, then there is formation of a carbanion, because there is a difference in the electronegativity of carbon and zinc. Zinc is much more electropositive as compared to carbon. As a result, a carbanion is generated in the reaction, which attacks the carbonyl carbon of aldehyde and forms this beta hydroxy ester. The reaction proceeds via the formation of zinc enolate, which then reacts with carbonyl carbon. As you can see here, this is zinc metal which we are using here. There is formation of zinc enolate. Zinc enolate then attacks the carbonyl carbon of aldehyde and there is formation of this product. Beta hydroxy esters formed as a result of Reformatsky reaction undergo dehydration to form alpha beta unsaturated ester. The dehydration is facilitated because the product has conjugated double bond system, which is stabilized by delocalization of pi electrons. As you can see here, this is beta hydroxy ester and this easily undergoes dehydration to produce alpha beta unsaturated ester. The driving force for this reaction obviously is a stabilized system. Stability is incurred into this molecule because of the delocalization of pi electrons, because of the conjugated double bond system. Reformatsky reaction is given by organozinc compounds, but not by organomagnesium compound or organocadmium compound. As you know already that as organozinc compounds are organometallic compound, organomagnesium and organocadmium compounds are also organometallic compound, but even then Reformatsky reaction is given only by organozinc, not by organomagnesium or organocadmium. We have to find out the reason for this. Zinc enolate does not react with ester, hence self condensation between two ester molecule does not take place. The reason is, first reason, that zinc enolate does not react with the ester and hence self condensation does not take place, and that is why we do not get multiple products. Zinc enolate reacts with carbonyl compound to give desired product. So, these are the two reasons why Reformatsky reaction is given by organozinc compound. Now, you will see that in these lines we will discuss why organomagnesium compounds are not appropriate enough to undergo this Reformatsky reaction. See, magnesium is more electropositive than zinc and is highly reactive. Hence, organomagnesium compounds undergo self condensation reaction between two ester molecules. As a result, multiple products are formed during the reaction. In case of organocadmium compound, cadmium is less electropositive than zinc and that is why it is less reactive. Hence, organocadmium compound do not undergo condensation even with carbonyl compound, that is our desired product, and that is the reason that organozinc compound are the best ones or best organometallic compound to undergo this Reformatsky reaction. Now, we will discuss a few application of Reformatsky reaction. The reaction is used in the preparation of citric acid starting from oxaloacetic acid. You can see here, this is oxaloacetic acid undergoing reaction followed by hydrolysis to give citric acid. Another application of Reformatsky reaction is in the preparation of beta hydroxy beta phenyl butyrate starting from acetophenone and bromoethyl acetate. We will now discuss Tishkianko reaction. This is a very interesting reaction in which the aldehyde, which may or may not have an alpha hydrogen, it does not matter whether the aldehyde has an alpha hydrogen or not. This aldehyde in presence of aluminum alkoxide or magnesium alkoxide undergo auto oxidation and reduction. One molecule of aldehyde is oxidized to carboxylic acid and the other aldehyde molecule is reduced to alcohol. Then the carboxylic acid and alcohol so formed react together to form ester. That is, as a result of reaction of an aldehyde in presence of this aluminum alkoxide, we find that there is formation of an ester moiety. Starting from aldehyde, we are able to form an ester with the help of Tishkianko reaction. Benzaldehyde forms benzyloxybenzoate when heated in sodium salt of benzyl alcohol in 90% yield. In the mechanism of this reaction, the alkoxide acts as Lewis acid to coordinate with one molecule of aldehyde and to facilitate the addition of a second equivalent of aldehyde generating a hemiacetal intermediate. This species undergoes an intramolecular 1,3-dihydride shift that results in the formation of ester. As you can see here in this figure, there is intramolecular hydride shift and there is formation of this ester molecule. Now, to summarize today's lecture, we have discussed Beckmann rearrangement, we have discussed the mechanism of Beckmann rearrangement, and then we have discussed various application of Beckmann rearrangement. The most important application of Beckmann rearrangement is in the synthesis of nylon 6, which is formed by the polymerization of caprolactam, which in turn is produced by the Beckmann rearrangement of oxime of cyclohexanone. Then we have discussed Novengiel reaction, its mechanism and some application of Novengiel reaction. We have also discussed Reformatsky reaction, its mechanism and some of its application in the present lecture. And lastly, we have discussed Tishkianko reaction and its mechanism. In the next lecture, we will discuss some more reactions undergone by